Oh, right. So yeah, I'm almost done with the convex stuff. Then we will move more towards the real topics of this course. So yeah, so the point was if you end up having to solve problems with eigenvalues mostly, or determinants as well, this kind of things, like operations on matrices that sound very complex, there's often a way out via SDPs. Yeah, and SDPs, unlike simpler convex problems like LPs and QPs that you can solve fairly easily nowadays for very, very large problems, SDPs are a bit more difficult for very large problems for actually very, very technical reasons, but it's often feasible anyway. Okay, an interesting observation is that actually all these problems are kind of like the same in the end, in the sense that you can always write an LP as a QP as a QCQP, QCQP as SOSP, and SOCP as SDP. So you have this kind of inclusion. So in principle, every problem is an SDP. You can put it that way, in the sense that SDPs include everything. However, don't turn an LP into an SDP just thinking that if anyway it's an SDP, I can do that. Why? Because when you actually call a solver that will handle your problem, the solver will change a lot depending on what kind of problem it is. And an LP solver is a completely different beast than an SDP solver. So if you're turning an LP, for example, into an SDP, you're basically shooting yourself in the foot by making a simple problem a difficult one. But it's good to know that. Okay. Yeah, some solvers, there's a lot. So LPs, you have a number of solvers. Gurobi can also handle MILPs, if I'm not mistaken. QPs, you also have a lot of things. And what is maybe a bit more recent, you have a number of QP solvers that are designed to solve QPs arising from optimal control. So we'll see that in the lectures, that when you form optimal control problems, the QPs that you get in the end have a very, very specific structure that can be exploited. So you have a bunch of them nowadays. There's a few more. They're like competing for speed mostly. So how fast can we solve this QPs, SOCPs as well, SDPs? You have some solvers to do that. Yeah, and you have also a bunch of more like modeling environments. So it's not so much about the machinery that is in the computer for solving the problem than writing down your problem. So writing the cost function and constraints. And what people have observed is that it's a bit difficult to just ask your design a code that will just kind of spot that your problem is convex regardless of how you write it. Like say you write your problem in a very, very clumsy way, and the computer will somehow disentangle that you're actually trying to solve a convex problem but you did not realize. We don't know how to do that. So what people have done is change this problem into actually putting on the user the burden of writing a convex problem. But he's doing that in a smart way, in some sense, which is it will force you to write the problem in such a way that it has to be convex in the end. So it will limit you in how you use the functions that you put in the cost and constraints to be convex and to be convex operations or convexity preserving operations, so that you end up with a convex problem. So it's called disciplined convex programming. So the structure of the programming language forces you or disciplines you into writing convex problems. So yeah, if you learn how to use this language and respect the disciplined convex programming approach, then you have a convex problem by construction. yeah, that's basically the main thing to remember. So how do you get the convex problem, convex cost function, convex inequality constraints, and affine equality constraints? If you have a convex problem, you have global optimality. Yeah, you have a few books on the topic that you probably actually know about already. All good with that? Yeah, so it was just a primer on convex stuff, and as a matter of fact, I will not talk about convexity again, because most often we don't have convex problems in optimal control. The only instance when we have convex problems is if we have linear systems. So if you have linear dynamics and convex inequality constraints and convex cost functions, then you do have a convex problem, like linear MPC. It's a convex problem you have in the end. But if you solve more complex optimal control problems arising from generic ODEs and so on, you can usually forget convexity. And we have to live with that. And it's not such a big drama, actually. Okay, so maybe just a short introduction on what we will be trying to do in the course beyond what has happened so far. Maybe just the whys and some remarks. So while we do optimal control, we have kind of moved from let's make the system work to let's make the system work as efficiently as possible, for obvious reasons. I mean, economic, energetic, and so on. And there's been a quite impressive evolution in optimal control, I would say, over time. If you went back 30 years ago, okay, that's quite a bit in time, but I mean, it's not that far in the past in some sense. Only very high-end application were using optimal control was used in shooting rockets, for example. How do you get in orbit with the minimum amount of fuel? And I was pretty much limited to do that a bit in the very large processing industry. 20 years ago, it was possible to solve simple, not too large optimal control problems on a desktop computer. And then the focus shifted a bit. So heavy industry like oil industry and big processing industry was getting interested in solving or optimizing their processes. 10 years ago, the shift was towards larger problems, solve faster. So you could solve now fairly more difficult OCPs in seconds to minutes, on the desktop computer. 5 years ago, we started talking about millisecond range for solving OCP. So that's a short time to actually move from seconds to milliseconds. And we started talking about deploying these techniques on embedded applications, like put it inside a machine that moves. And now we're talking about microsecond range in some application. And I've seen part of that shift. I mean, when I was a young student, I could see the iterations on my OCP going you could see that happening. And today it's just, it doesn't take anything. So I've seen part of that. So I think it's quite impressive. Part of that, of course, is due to the fact that we have more powerful computers, but that only explains a fraction of this progress. Actually, what really happened is that people figured out how to do it or solve these problems efficiently in the computer. So how to use the resources in a good way. Okay, just on the notation, I hope it will be as clear as possible. I try to be a bit disciplined. It's not always possible, but I will generally try to use this notation. So the italic notation for scalars and the bold notation for vectors. Sometimes we have collections of vectors. Sometimes you just collect all the variables as a kind of big group of things. Capital letters for matrices. This is annoying some people sometimes, so I hope it will not be problematic here. So this is normally the gradient operator with respect to x, and the Jacobian. del x. But I will abuse a little bit the notation and essentially use also this for Jacobian transposers essentially. So when you have a gradient, this would just be the transpose of that one. But then if you work in multivariable, it can be useful to use the same notation, essentially saying a Jacobian transpose. Don't think I'll use that one in these lectures actually. Yeah, Nabla 2, that's the Hessian operator. I've used it before actually. We'll work with mostly ODEs. I will talk a bit about DAEs a bit later in the course, I think. But essentially we'll play with this kind of object, x dot given by a function of xu. And that may be a very nasty thing. You may have 100 states behind this f function, for example, or more. But yeah, it will be the shorthand. And we'll talk also a lot about discrete dynamics, because as you'll see, essentially the trick we play in optimal control in the numerics is to move from ODEs to discretized dynamics and solve that. And this will be two norms, as I've used already actually. Okay, some examples of OCPs, optimal control problems. You may have discrete problems. Yeah, so that's essentially what we will be doing. Start from the this continuous OCP, knowing that there may be very strange things happening behind that. We'll make some approximations and turn that object into an NLP, a nonlinear program. So we'll have a discrete set of variables, W, it's something in Rn, an objective function in equality constraints and equality constraints. And once we can form that problem, we will basically use an off-the-shelf NLP solver to solve this problem. People call this step here, going from here to there, typically transcription or discretization. You'll find both words in the literature. And there's really a lot to unpack in this transition, because there are different ways of doing this, yielding different properties and different NLPs. Why is that not trivial? Because everything is mixed up. Essentially, everything is connected to each other. So you'll make a choice of how you go from here to there, how you transcribe your problem, the transcription strategy. But this choice will have a very big impact on how easy it is to solve this NLP and how reliable is it to solve this NLP. And the other aspect is that your choice of transcription will also dictate what kind of tools you will use to solve the NLP. You may not want to always use the same tools depending on how you do it. Another aspect is that when you transcribe your problem, this NLP will typically be very large, but it will have a lot of structure inside. We'll see what that means, and that will also dictate how you will solve it numerically in the computer. So this progress I mentioned, like going from seconds to milliseconds to solve an optimal control problem, it's really coming from identifying these structures and using them properly. Yeah, and at the end, in practice, the choices you make in this chain from the problem, the transcription, and the NLP solver, that will typically depend on what you actually want to achieve in the end. Do you want a solution to your problem? Do you want to be reliable? Do you want to go real time? And so on and so forth. Yeah, so we'll try to understand a little bit these questions in this course. And so the big picture is we'll discuss the transcription, how you go from continuous to a discrete problem, NLP, discrete problem. And then we'll discuss how you solve the NLP problem, because that's very important as well to understand how it's solved. You will call an off-the-shelf NLP solver when you want to solve your problem, but if you don't understand how that thing works, that will be very complicated to understand what goes wrong when it does go wrong. And I think we'll have some time to talk about some advanced topics, which are also quite interesting. Okay, so I use this map usually with my students to help them understand what we're talking about. Because essentially the numerical optimal control is really a kind of a big thing with many different boxes, and if you are not sure of where we sit, what we're talking about, it's good to go back to the map. So I'll go back to this thing a number of times when I move from one topic to the next. But essentially the tool chain, when you go from an optimal control problem to solving it, will be this. So you start from your problem, that's your set of equations, your ODEs and your constraints, and then you have to do the transcription, so go from an OCP to an NLP. And there you have different paths. We'll talk about these three different things: collocation, single shooting, multiple shooting. There are different choices of how to write the NLP. And at this stage you have an NLP. It may have different structures and properties depending on which role you have chosen, but it's an NLP in any case. And then you have to pick a technique to solve it, and we'll be talking about interior point and SQP in this course, which have there are different ways of approaching the problem. They're also connected in some ways. And we will talk a little bit about that at some point. Once you choose SQP, you have still different approach to solve it. So I'll go back to this map. I hope it's kind of clear enough? If you want to ask questions to help you understand. Yeah, okay. So we're supposed to stop at 11, but we can get started on the Kkt conditions. Okay, this will keep us busy until tomorrow, I think. I'm just curious, anyone knows about what Kkt conditions are and what they stand for? Yeah, okay. Do you know everything about it already, or yeah? Yeah, we'll see. So if you know lots, then you may find this a little bit easy. If not, then you may learn something. So it's kind of far away from the OCP question, but it's a very important thing to understand properly. Whenever things go wrong doing optimal control problems, it's often related to something that happens in here, in this machinery that is hidden quite far below the optimal control problem. And that will be important to understand them. Once you understand them, it's often fairly easy to understand what the NLP solver is talking about. It's like, you know, giving you all this reports and you know, displays when you call it. It's a bit easier to understand that once you understand the Kkt conditions. Yeah, so that's the menu. We'll talk about these things. And it's not very clear where I should put the Kkt conditions in this map, but essentially what happens is that when you call one of these methods to solve the NLP, these methods will essentially try to solve the Kkt conditions. It's a bunch of algebraic equations essentially that you're trying to solve. And when these guys struggle, it's often because the Kkt conditions are a bit badly posed. Yeah, so but that's the main point. So NLP solvers are essentially Kkt solvers. They basically work on these equations and try to find a solution to them. So that's essentially what's happening. And if you have the clear picture between what it means to have an optimal solution and what it means to have Kkt conditions satisfied, then you understand much better what's happening. Yeah, and that's actually an interesting observation. It's going much higher back to the OCP, but you can actually easily write very, very simple OCPs that create very, very severe difficulties at the Kkt level. I can give you some example at some point if you want, which in turn will make your best off-the-shelf NLP solver struggle a lot. So that's easy to create. Okay, we'll start from the basics. So we looked at this already, but so that's an NLP cost function, equality constraints, inequality constraints. I will stop assuming that anything is convex in here. That's not the point here. If it is, it does not change the message, but it may not be convex. I will most often assume that these functions are sufficiently differentiable. So I'll stay away from non-smooth function or really non-differentiable functions. At least first and second order derivatives should exist. Yeah, the W's, we call them decision variables usually. And one thing that is useful, if you take a feasible point, so feasible point would be a point that satisfies this. We'll talk about active set and active constraints, and essentially that's simply saying or checking which of these guys are at 0, right? If some of the h are less than 0, we call them inside the feasible domain, and then we call the corresponding constraint not active. And if one of the h's is meeting the 0, we call it active. And if you collect the set of all the active constraints, we call that the active set. I'll use this strange A to note that. And I'll show you at some point that there is a notion in between active and not active, which is actually quite important in a number of contexts. Yeah, convex problem, we discussed that. I'll assume smooth, well, not necessarily smooth, but at least twice continuous, twice differentiable functions. And well, there is one subclass, the mixed integer problems, where some of the w's may take discrete values. You can think of gear shifting, for example. Huh? It's not an abstract problem. You have lots of mixed integer problems. But I'll not talk about that. That's it calls for another level of optimization when you have to deal with that. Yeah. Okay, a few minutes left. Okay, feasible set. Simple. That's the set of points that satisfy the constraints. Not much to say about that. Global optimum is going back to what I briefly mentioned before. And I'm not talking about constraints. Well, yeah, actually I'm here. Global optimum is really the point W star that has a better cost than any other point in the feasible set. So that's an interesting thing. So the optimal cost, so really the lowest possible phi that you can get, that's a unique point. You will not achieve more than one. I guess it's quite obvious. However, of course, the W star may not be unique. You may have different points that achieve exactly the same cost. And an example would really be a cost function that look like this, right? With a flat domain here. Actually, you even have a set of solutions here. And that's actually not that uncommon, even in practical problems. Yeah, you can have unique optimal solution. You may have different optimal solutions, and you can also have no optimal solution. If I give you an LP problem with this cost function and no constraint, then it's not lower bounded, right? So if you call a solver on that guy, you will probably stop at some point and say, well, it looks like your problem is unbounded. I'll finish with that, I guess. So I briefly talked about that, the notion of local optimality. That's really essentially this picture is summarizing everything. You have essentially local minima here. And you can formally pin a definition on that. And roughly speaking, what we are trying to say here is that a local minima is some place in the function where the neighborhood is larger, but not necessarily the whole function, right? So anywhere around this point, if I check in the neighborhood, this n delta, I'll find larger points. But if I go beyond that neighborhood, I may actually find better solutions, for example, down here. Yeah, that's one important thing. If you're trying to find the global optima of a function, you are trying to find a local optima anyway, because if you have a global optima, it's also a local optima by definition. And when you call NLP solvers, they are essentially doing that. They are not trying to find a global optimum, never. They are trying to find something that satisfies the conditions for being a local optima, and then you hope it's also a global one. Is that clear for everyone, or yeah? Okay. One obvious but important thing, because I will use this in building the complete picture. What it means to be optimum is essentially that if you take any direction d inside the feasible set, and let's say some constant, possibly very small, that is positive, then if you move along that direction, the cost will increase. So this phi of W star plus alpha d is larger than W star, right? Should feel kind of obvious here. If I'm at that point, the feasible directions would be basically the neighborhood. And if I move along these directions, the cost function will increase, right? But the definition is a bit, more generic than it sounds. If I have, say, a function that looks like this, right? And I put a constraint here, then this point, for example, does not satisfy gradient is 0, but the only directions where I can move are these ones, right? And if I move along that direction, I increase the function. So that's a definition that can support the construction of optimality conditions also with constraints. Okay, so we'll continue on that in the afternoon. And yeah.
What time?
Yeah, right. I propose that we start at 1 because we have to stop at 2. So we at least have 1 hour. Yeah.